All right, for this new reaction, it's actually just like what we just saw in reaction 7, the halogenation, just like that. Okay. All right, let's see what's going on. Or what's different from the halogenation. All right. So right now we're adding, of course, halogen still, chlorine or bromine, right? Cl2, bromine 2. But this time we use nucleophilic solvent like water, like alcohol. Contrast to, let's compare and contrast. This is just a halogenation we saw earlier in reaction 7, all right? So we add halogen and a non-nucleophilic solvent, could be a carbon tetrachloride or chloroform, CHCl3, all right? So it doesn't do anything basically, but this guy is a nucleophilic solvent, so it got lone pair and oxygen. They can do something, they can participate in the reaction. Now, let's look at the difference of the product. Right, so anti-addition, same thing. Yeah, so pretty much the same mechanism. Just replace one of the X with the nucleophile. That's if you use water, you get an OH. If you use an alcohol, you get an alkoxy group on the carbon. Right? But the stereochemistry is still the same because this is the same reaction basically. All right. All right, let's take a look what's going on. The first step, let's say you add chlorine, you get chloronium ion. You add bromine, you get bromonium ion. All right, and now solvents mean the majority of molecules of compounds are solvent. So solvent is like running around everywhere. So instead of this chlorine come attack, we have much less solute than solvent, right? Solvent gonna compete that. Solvent will come in attack on to one carbon on the backside attack is at SN2, go to on this is on wedge. So alkoxy group will go on dash. Yeah. And then deprotonation, you know that, you get the product. The other carbon can be attacked as well. So alcohol comes in, attack at the other carbon. That should be on wedge, this should be on dash. That's why it's weird. There should be dash right here. And then deprotonation, you should get dash, this is dash, all right? Right there, that's the enantiomers. Same mechanism, right? And what controls the stereochemistry? The halonium, 3-membered ring halonium intermediate right here. All right, let's see the stereochemistry of anti-addition. Same thing. All right, the OH is going to go. Now, in the case that the two carbon are different, right? If you go back here one more time, these two carbon are the same thing, right? These two carbon are the same. So alcohol can attack here, Doesn't make any difference. There's two products there. But now, these two carbon have different substituent on it. All right. What's going on? The water in this case will go attack at the more substitute carbon. Again, just like Markovnikov, just like that. Right. This is not really Markovnikov, but like it looks like nucleophile usually and tends to attack the more substitute carbon. And here's the reason why. Let's take a look. All right. When bromonium ion is formed, like that. Now, water can attack on this carbon, right? From this is just a transition state. Oh, we'll get back to that. And water can attack that too. You get another transition state. If you look at the transition state right here and compare the stability, more substitute carbon, better stabilize positive charge, right? Less substitute carbon doesn't stabilize the positive charge as well. You might ask, how does it get positive charge here? Well, it doesn't really get positive charge. It gets partial charge. So what's going on here? There's a bond forming and bond breaking right here. The positive charge are transferred from bromine to water, right? So right before attack, bromine is positively charged. Once it attacks, there's a transition state like before become the product. The positive charge of bromine are being transferred to that carbon to that water. All right. Same thing. If water want to attack from this side, the positively charged bromine that's before, during the attack, the charge will be transferred to that carbon to the oxygen. So that's why they become partial positive here, not a full charge anymore. All right. Now, when a carbon get positive charge, who stabilize the positive charge better? Of course, the more substitute carbon, right? Because hyperconjugation and whatsoever. All right. So this attack at this carbon, the more substitute carbon, we have a more stable transition state. So lower activation energy. Right. So stable transition state means lower activation energy, and the process of making this guy is much faster than the other one. So that's the reason why water, the nucleophile, will attack on the more substitute carbon. Right? So go further, you get that. So attack from the back. So bromine comes out, water is going to be on the dash line. Right? Some of you get confused right here. So we already have the methyl at the dash. Well, this is SN2. When SN2 attack, it will push anything forward. So this methyl going to go forward when once water attack. Right? Water going to be on the dash, and this methyl going to come to the wedge. So right there, backside attack basically, and then deprotonation. Yeah, you get enantiomer right here too. There's a 2 chiral centers. You get enantiomers, and then you get 2 enantiomers at the end. Okay, so that's a stereoselectivity. So water on the nucleophile will selective to the more substitute carbon. Basically, that's the point. All right. In the transition state, the carbon bear partial positive charge. More substitute carbon stabilize the positive charge better. Okay. All right, let's review all the reaction together. Do this practice together. All right, so first one, predict the major products. What we get, this is acid catalyzed hydration. So Markovnikov, it will pass through a carbocation. So watch out, rearrangement and what's the other one? Racemization. If you make a new chiral center. Always going to go on to the more substitute carbon. That one, you should get that. All right, so no rearrangement there. This is stable carbocation. Next one is hydroboration oxidation. So this go anti-Markovnikov. Boron going to go here, and then will be replaced by an OH later. So anti-Markovnikov go that right there. So this is a new chiral center. So you get 2 products. All right. All right. Next one. This one hydration with Markovnikov. Right. Markovnikov orientation. So OH going to go to more substitute carbon. All right. You should get that. Not a chiral center. So we're good. Next one is just catalytic hydrogenation. Add hydrogen onto alkene, across alkene. Remember though, this is a syn addition, so hydrogen get added on one side, right? But there's no chiral center here, so don't worry about it. Next one, so this is halohydrin formation. So add halogen first from bromonium ion, right? And then water attack at the more substitute carbon because it's more stable there. You get that right there. So there's a watch out for the nucleophilic solvent. Next one, carbon tetrachloride, so non-nucleophilic solvent. So bromine just add on to it, and then another bromine attack. So you get anti-addition there. All right. I don't put a squiggly line on here, or because this is not a chiral center. All right. And yep, that's pretty much it. We have class activity 3, question 1, 2, 3, and 4. And the answers. You know the drill. All right. Good luck, guys.